Hi, in this video we will see how we could tune the PID controller by the Flower Pollination Algorithm, which is one of the swarm intelligence optimization. Now previously we explained if you have a system and controller and your system has like actual outputs and you would like your system to follow this desired output or the set point or the reference. So we will have to use the controller. And now we focus on the PID controller. Now we need from that controller to improve the performance of the system so that the Y, which is the output of the system, follow the R, which is the reference or the set point. Now the closed loop feedback system, which is consists from the controller and the system. So this is the feedback. The error is applied to the controller, and then the controller generates the control law, which is submit to the system in order to improve the performance of the system. Now we already have been said all of that. Now we consider that you have the system, the transfer function of the system, and then we will see how we could tune the PID. Now just a quick refresh, we said that the PID controller is very simple and available everywhere and have successful history, and it consists from three terms: the Kp multiplied by the E, the Ki multiplied by the integral of the E, the error, Kd multiplied by the derivative of the E. Now, if you need more details about PID controller, you can see this in my channel. Now, this is the control law of the PID controller. Now, consider the following problem. You have this transfer function, and you would like to design a PID controller, and you need to tune the PID controller using the flower pollination algorithm. Now, the tuning process of the PID controller is the key of how to use the PID controller. Selecting the Kp and kpikkd, it's usually based on the trial and error. But this way of choosing the Kp, kpikkd is consuming time. And that's why we would like to convert the tuning process into optimization problem, and then we just use any optimization technique to solve this problem. Now, just quick refresh also about the optimization problem. Optimization problem is to find the best solution among all feasible solutions. Some terminology, we need to understand what the objective function. So in our problem, which is we need to minimize the error. So we will use this index, which is the integral time of absolute error. So this is our index. Now we need to the optimization technique to find the value of Kp, Ki, which is reduce this term, which is the integral time absolute of the error. Now, what's our decision variable? The decision variable is Kp, Ki, and Kd, and also we need the CRT space, which is the lower and the upper value of the Kp and Ki and Kd. Now, flower pollination algorithm. The basic concept of flower pollination algorithm, it's a swarm intelligence inspired from the pollination phenomena in the flower. The main idea of the pollination in the flower is to transfer the pollen from the male to the female. Now, the pollination could be classified on the way that the pollen is transferred. So we consider there is self-pollination and cross-pollination. So self-pollination, which is the pollen fall down from the same flower, and the cross-pollination that the pollen have been transferred from other flower, like by wind, by insect, to another flower. So this is the two way of the pollination: the self, which is this happening the same, and the cross, which is by two flowers. And based on this strategy, we will assume that the cross-pollination is the global, so the cross is the global pollination, and the self-pollination is the local pollination. In order to switch between this algorithm, these two mechanisms, we will have like switching probability, and this is selected by the user. What you want more, self-pollination or cross-pollination? Now, the key term of the flower pollination algorithm is first the pollen, which is the possible solution, the individual solution, then the pollination, which is the population and the group of pollens. We need to define the search space, the lower and upper bound of all the possible solutions. Now there are two processes, the local search and the global search. The local search, which is the same as the self-pollination, and the global is the cross-pollination. And then we need to have the switching probability, which is to switch between these two mechanisms. Now, the procedure. The first stage is the initialization, which is that you have n of the population, and you need to set these values. So the basic equation for the initialization, so each pollen or each flower has the value based on this equation. So this is the lower bound plus random value multiplied by the difference between the upper and the lower. So imagine you have this this population, and this is like the random value we just give to our population. Then we need to evaluate the objective function, and we said that in order to tune the PID controller, we will use the time integral absolute error. So imagine that you put each of this x, which is the kpikkd in our case, and then you just find this, which is the evaluation of the individual position of each parameter. Then we have to sign the xg, which is the best solution, give the minimum, because we are looking for the minimum. So in our case, this is the objective function, so it's clearly that this is the xj, which is give the minimum objective function. The next stage is the loop, which is the iteration. Now we need to select a random value by the algorithm, and then we compare this random value with the switching factor. Now if the random value is less from this, which is the switching factor, so consider we have 0.5. Now we assume that we will do 0.5, 0.5 self pollination and 0.5 cross pollination, or let's say global search and local search. So if the random value is 0.3, 0.1, which is less from the switching, so we will perform the global search. So we need to decide the step size, which is how much we jump from our current stage to the xg, the best solution we found. Now you could use any let's say any strategy to decide the step size. Like for example, you can generate it by random value, you could generate it by the fly distribution, Gaussian distribution. So you could just set fixed step size. It's up to the user. Then we use this equation, which is for the global pollination. So the next position of is the current position and multiply by step size and the difference between your current position and the x, which is the best position you already found by the algorithm. Now in order to improve the performance of the algorithm, we could use also, so imagine that you are in this xi and you need to be close to this xj. So this is the equation in order to move towards xj, which is the best value of the function. Now in order to improve the convergence of the algorithm, you could use this instead of this. So instead of have xi, you could use xj as the beginning, and then the difference between your current and the xj. It's up to you to use both of these equations, but from my experience, this gives better convergence. Now, if the random value is larger than the switching, so for example, 0.6, 0.7, 0.5, so let's say it's equal or more than switching factor. So we will perform the local pollination, which is also the next the update position, which is the current position, and also this is the step size, and the difference between two pollen just selected from the population like randomly. So for example, you choose this xj and xk, which is randomly, and then so this is like a random search. Now in this search, which is the global search, you search for the best value. However, sometimes when you do random search, you could find like better solution. So this is the balance between you follow the best solution you already found by the algorithm, or you just select two random value and try to follow these two random value. And again, you could improve the performance of the algorithm by using xj as the initial search, and then you just select two randomly from the algorithm, from the population, and then you move toward these two in order to explore the search space. So in this, you just explode around the xj. Here you explore the CRT space. Then you update the population and you update the objective function, and then you just perform the greedy selection, which is to select the new xj. After you finish the loop, you go to the termination. So there are two strategies for the termination. Either you just repeat until you find the maximum iteration, or you just convergence. So there's no any better solution found by the algorithm. Now the parameter that need to be set by the user is the population size, the initial position, the switching probability, the step size, and also you have to use the random value and the termination. So the pseudocode, first you put the objective function. You need to know what's the objective function, the population size, the switching probability, and the number of iteration. We go to the initialization, so you initialize the population, and then you evaluate to find the xj. And then you go to the loop, so the first loop for the iteration, the second loop for the population, and you just to switch between the global search and the local search, and then you update and you ask if the iteration is finished or not, and then you print the optimal value. So let's jump to the MATLAB to see how we could perform the tuning of PID controller using flower pollination algorithm. Now, in the beginning, this is CLC, clear all, close all, which is CLC to clear the common window, clear all to clear all the value of the parameter, close all to close any window opened by the MATLAB. We will use simulation time like 20 seconds. Now, if we go to our problem, so this is our transfer function. So the coefficient of the numerator is 1 and 2. So this is 1 and 2, and the denominator is 1, 2, 3, 5. 1, 2, 3, 5. And then we use the command TF, which is transfer function. So the G, which is the open loop of the system, TF, and the coefficient of the transfer function. And here we just simulate the open loop of the system, which is first you divide, we decide the simulation time, which is with the step size, and then we give our input to the system, which is unit step input, and then here we just plot, we simulate using the LSIM, and here we plot the output. So this is the time, this is the output, and here the color and the line width, and the time is the X and the amplitude is the Y. Now if we just perform this without any controller, so this is our response of the system. As you can see, we apply step input and the system has oscillation and it's also not stable, and it's required to controller and to improve the performance of the system. And also we could have, like, for example, unstable system. So if we just run the code again, you could see that like your system is unstable. So we will see how we could use the PID controller tuned by the flower pollination algorithm in order to improve the performance of the system. Now this is the parameter of the flower pollination algorithm. So this is the number of pollination, and I just put 10 in order to short the runtime. This is the iteration number of iteration. This is the step size C, 0.5, and this is the switching factor, which is also 0.5, and this is the number of variable. We have 3 kp and ki and kd. And this is our CRT space, and you could set any CRT space is depend on your problem. So the minimum is 0, the maximum is 50, and this is the counter for each iteration. This is our reference value, which is 1. Now the initialization, as we said before, so in the initialization, so we use this formula, which is the lower bound rounded multiplied by the difference between the upper and the lower. So as you can see, so this is the number of how many variable you have, and this is your position. So randomly have been set to all the number of population. Now, because we have 3 variables, kpi, kkd, so this is I, which is the population, and this is the 1 for the first variable, the second variable, the third variable. Now we use the command PID in order to set up the transfer function of the PID, and then we use the command feedback multiply. So we are just doing this now. So this is the transfer function of the controller. This is the transfer function of the system. We multiply this, and feedback is unity feedback. So we just multiply the K, so the G of the controller by the G of the system, and this is the feedback, which is 1. And then we simulate. So this is the time, this is the unity step, and this is the simulation of the system as a closed loop with the PID controller. And then here we just evaluate. So if you go here, so you just evaluate the objective function. So you are evaluating the objective function, and we use this formula, integral absolute time error, which is the difference, the error multiplied by the time. So you could see, so this is the difference between the current value of the y and the reference value multiplied by time, and we just sum it because integral. And then we find the best. So if you go here, we said assign xg, so we need to find the minimum, the x, which is give the minimum of the cost function or the objective function. So here we find the minimum, which is the three terms, kp and kd and ki. After you find the xj, we go to the loop. So we are now in the loop, and we perform first. So we just generate random value, and we compare the random value with the switching. So if it's less, we go, as I said, I use this equation, which is xj, and the difference between the current and the xj. So xj, and this is random multiplied by the c, which is the step size, and your current position, and the xj. And just to check the boundary if you are in the limit. And if it's else, which is less, large than the switching, so we perform the other searching, which is we select 2 from the population randomly, and we just say that xj is the random multiplied by the step size, and this is the 2 which is randomly. So here we perform the exploitation search, and here we perform the exploration. We just explore the searching space, and after that we again put it to the model, the kpikkd, like update the new value, and we just simulate the response, and we find the cost function, the new objective function, and we choose the minimum. So you compare with the what we already saved. So if you find something minimum, so you just replace it, and if you don't find, just keep the best you find. And here we just plot the cost function with each iteration, and finally we just plot the final value and the final simulation of the system. So we have a system, we apply PID controller, we tune the PID controller by the Flower Pollination Algorithm. So let's run the system, the code. So this is the, as I said, and this is the system after. You could see that the performance is not good because we just have not too much population. So as you can see here, number of population, number of iteration is just 10 and 20. You could just increase the value in order to improve. So we see here from this simulation that even if your system is unstable, look, even if your system is unstable, the PID controller tuned by the flower pollination have already been stabilized, and as you see, the error steady state is 0, and this is your convergence. So you start from error, and then you go to the minimum error. Now also we could change the system, like as it can be in the beginning, which is the oscillation system. You can see again that the system is already stabilized and the performance of the system have been improved. So the objective of this video is to see how we could have a system which is not follow our objective. The performance of the system is not good, and we apply PID control to that system, and we have the transfer function, the G, the open loop of the system, and we apply the PID controller. And in order to overcome the problem of tuning PID controller, we just use the algorithm, flower pollination algorithm, and we have already seen that the performance of the system is improved. Thank you.